But with odometry, if an obstacle or another robot happened to take it off its course, it would be able to find the correct path to go and reach the location it needed to go to. And it helps with path finding, motion planning, and obstacle avoidance. So as you can see, this is a field mapped as an X and Y coordinate plane. What we want to do is imagine the FTC field as the coordinate plane and everything having its own X and Y position. And we want to use the sensors to find the robot's location. So now what sensors do we use? Well, we use encoders. Encoders, as you can see, are on the left, right, and bottom of the robot, and they're attached to dead wheels, which are also on the left, right, and bottom of the robot. And keep in mind that this odometry is for a mechanical drivetrain. So if you're using a different way of like wheels and movements, this probably won't apply. And we use dead wheels because for the encoders that are on the dead wheels on the left, right, and bottom of the robot, you could be asking why aren't the encoders on the mechanical wheels the if they're just keeping track of how much the robot moves. Well, because if the robot moves in place, the dead wheels won't move at all. So since the encoder's on the dead wheels, the location will be more accurate because if they're on the mechanical wheels and the robot was moving in place, the encoders would think your robot is moving around the field, having the location be inaccurate. So now let's position the three encoders. We have two vertical encoders on the left and right of the robot, and they measure the up and down movement of the robot. And we have one straight or horizontal encoder on the bottom of the robot, and that measures the left and right movement. So now we need to convert the encoder readings to distance. So encoders measures the number of ticks. So as you can see in the diagram, the encoder, which is the gray thing sticking out of the wheel, has gears inside. So a full tick is the gear's full rotation. So then we need to convert those ticks to a distance. So the distance is the number of ticks multiplied by inches per tick. And the inches per tick is different depending on your dead wheel size. And the way you find your inches per tick is by taking your robot, making sure it's a flat surface, and driving it 10 inches forward. Then you can see the amount of ticks your encoder read and do 10 inches divided by that number to get your inches per tick.
Great.
So now I'll be handing it off to Rohan.
Yeah. So just to make sure, are you guys clear on exactly what the positioning of encoders in odometry are and the ticks just before moving on? Okay. I got a thumbs up from Vincent. Is everybody else good? Okay, great. Uh, so now that we've defined the sort of structure we need for our robot, we can get into more of the math behind exactly how odometry works, how we take these readings from the encoders and convert them into our XY position on the robot. And first, we're going to define a few concepts before getting into the odometry math itself. So you guys may be familiar with radians, which you may have found out about in school. But the basic gist of it is that we want to measure all of our angles when doing odometry in radians instead of degrees. And if you look at this diagram here on the left, if we take an arc of length r, meaning we have this red line on the outside of the circle, that's the same length as the radius of the circle. So the two red lines here, r and r, are the same distance. That angle formed by that arc is 1 radian. And you guys may be familiar with this, but 360 degrees on a circle is equal to 2 pi radians. And from this point on, radians are going to represent all angles because they make the math for odometry much simpler than if we were to use degrees. And again, there's going to be no conversions between degrees and radians. Everything will be done in radians. So now that we've defined what a radian is, how do we calculate an arc length using a radian? So in other words, given a circle radius r and an arc length theta, so right here, this quantity r right here, we know the length, we know the radius of the circle and the angle theta shown in green. How do we calculate the length of the arc formed? How do we calculate the length of this red line? If theta were to be measured in degrees, this formula would be a little bit more complicated, but now that we have theta measured in radians, that's what we'll be using in the program. Arc length is just equal to theta times r. That formula gives you the length of the red line just by multiplying the two quantities. So that's another concept we just need to understand before getting into odometry. And finally, the last thing we need to get into is rotating a point about the origin. So put more formally, given an angle theta and a point xy, point xy is shown here in orange, and the angle theta is shown here in green. How do we rotate it about the origin, or 0, 0, to get this new point x prime and y prime? And this what's shown here on the right gives a way to derive this formula. Again, it's not too important. I'll just go over the details very briefly. If you have more questions about it, we can come back to it. But the essence is that you're converting from xy coordinates to polar coordinates, and then you add the angle and convert them back, and you end up with this final formula here, which tells you that x prime equals x cosine the theta of rotation minus y sine theta, and y prime equals x sine theta plus y cosine theta. So in your code, for example, you can think of it as a function that takes in your xy point and an angle theta that you want to rotate it by. And by using this formula, you can get a new point, x prime and y prime, that's rotated about the origin. Okay. So does that make sense for everybody? Are we good to move on from that point, or should we go back over anything? Is everyone good? All right, great. So now that we have these, these formulas that we've described, rotating a point about the origin, radians, arc length, now we're going to get into orientation calculations. In other words, how to efficiently determine our heading theta in radians. So which means the angle our robot is at relative to the rest of the field. And it turns out to do this, all we need are the vertical encoders. And one question that you might ask here is, why are we using the gyro to determine our orientation here? For example, the IMU on the Rev Hub. Actually, in practice, it seems that the response times for the Rev IMU are much slower than that of the encoder wheels, meaning that you have quite a significant degree of lag between when you get your IMU readings from when you get your vertical encoder readings. So to keep your odometry system as accurate and efficient as possible, you actually have to calculate headings from vertical encoders. It is possible with an IMU, but you have a much, much greater risk of inaccuracy. And that's what we've faced in the past as well. So by using two vertical encoders or vertical odometry wheels, you actually have a much more accurate odometry system. And to do this, the first key thing to do is to view these vertical encoder movements as arcs. So let's imagine the robot takes a random path on the field. This orange line here is quite arbitrary, but it just represents a path the robot could take. We want to zoom in on very, very small time scales, right? And on smaller time scales, you can effectively think of motor speeds as constant, right? In that instantaneous moment of time. The motor speeds are exactly constant. They're not shifting around right in that instant. And from that, you can think of the path of the vertical wheels, the path that they form, as an arc. And that's shown right here. If we zoom in at a very small moment in time on this orange path here, the robot is traveling in a very, very slight arc here because the motor speeds are constant. So that's the first thing. Uh, and just for reference, in future diagrams, uh, this uh, this image on the right is going to represent the same thing as the robot on the left. So this green square here means the same thing as what's shown here on the right. And the green circle is the center of the robot. It's just for ease of visualization. Okay, so the first thing we need to do is now get delta theta, or the change in theta from the vertical encoders. So this means uh, whenever we're at a certain point on the field and the robot moves a little bit, we want to figure out just how much the orientation of the robot changed, and we're going to call that quantity delta theta, or this triangle symbol and theta right here. And that's kind of visualized by this diagram shown here, keeping in mind that everything is constant because we're zooming into such small time scales, right? And you can see this arc that the robot forms here with D1 and D2. So now we want to ask, right? We know the quantities D1 and D2, right, which represent the distance that the left vertical encoder traveled and the right vertical encoder traveled. We know W, which is actually the width of the robot, and we want to figure out delta theta from those quantities. So we can define a system of equations using the arc length formula that we defined earlier. So right here, D1 equals delta theta times R minus W over 2. So here we're assuming that, W, that the center of the robot is, halfway between the left and right encoders. But we're saying, D1, this arc length right here, this orange dotted line, is equal to R, this big R here, minus the width of the robot over 2, right? We don't know what R is, but we know what the width is. So width over 2, that's a constant we defined earlier. And we know we can define the same thing for D2. D2 equals delta theta times R plus W over 2. And again, this is just the arc length formula. We have the radius of the arc, R plus W over 2, times delta theta. And using the system of equations, which is using the system of equations, we can solve to find a convenient expression for what delta theta is. After a bit of simplification and solving, we find that delta theta is equal to D2 minus D1 over the width of the robot. And this formula will prove to be very useful later when writing code and for future discussion. So just by taking the two values of the vertical encoders and by measuring the width of your robot, you can get the change in theta. And now what we want to figure out is how to calculate our global orientation from this local orientation. In other words, how do we figure out the angle of the robot relative to the field from this change in theta? And we can think about this as a continual sum, a continual process of adding the previous delta theta to the previous angle to produce the current angle. So if you look here, you have not delta, theta I plus delta theta equals theta final. So, when you repeat this process over and over again, right, you're adding small positive or negative increments, right, delta theta to theta I, which gives you an accurate estimate of what the robot's current orientation is. And again, like we addressed earlier, why we aren't using the IMU, which would be much more convenient, right? All you have to do is read the theta directly from the IMU, is mainly because of slow response time. So it's not going to be in sync with the rest of your odometry, which needs to be moving at a much faster pace. When I say moving, I mean it has to be responding and calculating your position at a much faster pace. So yeah, does that make sense for everybody, or should we go back and go over anything? Okay, I will move on then. So now that we know how to calculate the global orientation theta from our encoders, we need to figure out how to calculate R from the vertical encoders. That's that quantity right here, R. Uh, and using our formula for theta, we can actually find R because we know the arc length formula. D would be the average of the arcs denoted by D1 and D2. So these distances here, D1 and D2, you take the average and you get D. And using the arc length formula, we know that D equals delta theta times R, and rearrange, and we know that R is equal to D divided by delta theta, which we just received a formula for in the previous slide. So by combining those two equations, you can get a single expression for what R is. And this will prove to be useful later. Okay. So what we've defined earlier and what we've set up earlier is how to calculate our global orientation or the robot's global heading from just the two vertical encoders. So those two encoders on the left and right side of the robot. And we can get an accurate measure of our global heading. Now that we have that, we can move into the positional calculations, or in other words, how we determine our X and Y position on the coordinate plane that's the field. Okay. So again, like Isha mentioned earlier, the field is mapped as an X and Y plane, and we want to view this as a coordinate plane. And our goal here is to figure out at which point X and Y our robot is on the field. We already know the orientation, so now we need to figure out the X and Y. Again, like we mentioned, everything is happening on a very small time scale. And this math is constantly repeated to determine the position of the robot. So if you look here, similar to the global orientation, we take an initial position that we know the robot's at. So xi and yi. We add the changes in x and y that we're about to learn how to calculate. We add those changes to the initial position, and we produce the next or final position of not final, but we produce the next position of the robot, and that itself gets fed back into the start. We take that next position, add the changes, and get the subsequent position. So that's constantly repeated to maintain an accurate view of the robot's position. And again, the key here is to view vertical encoder movements as arcs on very small timescales. Okay. So the first question we want to ask is how we can use the data from vertical encoders. In other words, these encoders here on the left of the robot and the right of the robot to calculate change on one axis. So that's that axis you can see here in orange. Well, the movements here. And keep in mind that what we're about to show next does not account for the strafe encoder. So it does not provide a complete picture of how to calculate odometry, but we need to calculate things on one axis first. So we're going to calculate these changes as delta x1 and delta y1. And I'm going to put a diagram up here. D1 and D2 mean the same thing as they did earlier. D1 represents the distance that the left encoder traveled, and D2 represents the distance the right encoder traveled. And using D1 and D2, we can find delta, theta, and R. So let's say our robot started out at a certain point on the field, right? This green circle right here, this whole robot diagram here represents that initial position. So this whole axis, this whole coordinate plane is relative to where the robot is on the field. It's not relative to the field right now. So what it's going to be what's called robot centric, meaning the origin is at the same orientation as the robot. But now the robot's moved very slightly, and it's moved to this new point here, represented by this second diagram shown up top. And we want to figure out the change from this green point to this new, from the first green point to the next green point. We're going to call that delta x1 and delta y1. And that's effectively what we're trying to do here. However, we don't know what this new point xy is. So that's going to be the first step in our calculations. Well, we know delta, theta, and R using our previous formulas that we defined in previous sections. we're going to use those calculated variables to rotate r comma 0, the point that we know the robot is at using r, by delta theta about the origin. And we already know a formula to do that. We just plug these values into the formula and we get the point xy right here. So we know what xy is. Now we want to use that point to calculate the change in x and the change in y, delta x1 and delta y1. So this becomes more simple now that we know x and y. The formulas are just taken by subtracting the coordinates from each other. So delta x1 equals the original x coordinate r minus the new x coordinate x. So delta x1 equals r minus x. And delta y1 equals the new y coordinate y minus the original y coordinate, which is just 0. So the formula simplifies to simply y. So delta y1 equals y. So this gives us the change in x and y accounted for by the vertical encoders. And what's really cool about this coordinate-based method, there's actually other different methods that use slightly different concepts to handle this problem. What's cool about this coordinate-based method is that it works in all directions. And unlike these other approaches, we don't need any casework. And casework means like handling different cases when values are positive versus negative. We don't, just by plugging in the values through this approach, it works. There's nothing special that has to be done here beyond what we've described for this delta x1 and delta y1. And it works under any angle, configuration, etc. So we can use vertical encoders to calculate change on one axis. That's what we just did here. But how do we do the same for the strafe encoder on the other? The issue here is that we don't have two strafe encoders, so we can't use a very similar process like we did with the vertical encoders. Now, if you had 4 odometry wheels, you definitely could, but that's generally speaking impractical. And teams will stick with 3 odometry wheels just for ease of building and maintenance. However, keep in mind that the strafe encoder process is slightly different. So now we're considering this bottom encoder here. So if you go to the right, this bottom wheel right here. For the strafe encoder, what's especially challenging is when the robot turns. So we're trying to calculate the change in x and y accounted for by the strafe encoder. So when the robot turns, we get bad data from the strafe encoder. Right? Unlike the vertical encoders, we don't have two sensors that we can compare values of to account for turns on this axis. So for example, when we see the robot turn, in this example on the left, turn a certain amount and then move normally and turn the strafe wheel normally, we just think the robot should be recording, or the wheel should be recording the distance, the distance traveled, the distance represented by this dashed orange line. However, the strafe encoder doesn't know whether it's turning or not. So, the robot actually sees, that strafe encoder actually sees a straight line. And we have to figure out a way to correct for that. So how do we determine what this bad data is? As you can see, there's a diagram here on the left, which shows this bad data here in red, and the orange line, the good data, on the more to the top right. So zooming in on this diagram a little bit further, this bad data D forms an arc. And we know the angle and radius of this arc. It's actually delta theta and r, which we calculated earlier. R equals the distance from the center of the robot to the strafe odometry wheel, and delta theta was previously calculated. So using the arc length formula, which we know about, D equals R times delta theta. So the bad data, in effect, just equals R times delta theta, the data we don't want to consider when calculating X and Y. So we're going to use this formula to ignore faulty data. From the initial strafe measurement SI, which is represented by this solid orange line here, which includes the bad data that we don't want, right? We want to subtract away the bad data. So we plug in that bad data formula delta theta times r, remove that amount from the initial strafe encoder measurement Si, and we produce the good data, the data that's useful for us, SF, or the final strafe encoder measurement. So using this cleaned measurement SF, you can see it's zoomed in on that diagram from SF here, the dotted orange line just zoomed in a little bit more, and a few other symbols are thrown on there. Using this cleaned measurement, we can use some simple trig formulas to calculate our change in X and our change in Y. So we know delta theta. This delta theta is actually the delta theta we calculated previously. We say the change in X equals SF times cosine of delta theta, and delta Y2 equals SF times sine of delta theta. So again, it's just applying trig formulas right here to calculate the change in X and change in Y. So we now have calculations for all of the encoders on the robot. Using arc-based math, we have data for vertical encoders and we have data for strafe encoders, both calculated in slightly different ways. And just to reiterate why this is super important is when considering movements of the robot, right? If the robot moves, if the robot strafes and you have mecanum wheels, the robot's moving left and moving right. These vertical wheels right here don't pick up any movement because that movement isn't registered when those wheels are when the robot isn't moving vertically up and down. But the robot still is moving and its position is changing. So that's why this data from the strafe encoders are so important. And same something similar applies when you're moving up and down. The strafe encoder won't catch vertical movements. But now that we have these two robot-centric changes, how do we combine them? In other words, how do we combine this vertical data with horizontal or strafe data? All we have to do is add the vertical changes and the strafe changes because they're on the same axis. They're both on the same robot-centric axis. And we're going to call this quantity delta XR, which equals delta X1 plus delta X2, and delta YR, which equals delta Y1 plus delta Y2. But we're not done yet because these changes are robot-centric. We want to figure out our position relative to the field. So we have to convert these robot-centric changes into field-centric changes. And to visualize this better, we're on the plane here. We're on this local or robot-centric plane represented by the orange. We want to convert all the changes in X and Y on this plane to a field-centric plane, to a global plane that's relative to the whole field. So this in effect helps us account for any changes in orientation the robot's at, whether it's facing backwards, forwards, or any other way. So how do we do that? We want to rotate these X and Y changes onto the field-centric plane. And we already have a formula to do that. All we have to do is rotate delta XR and delta YR by the global orientation. I'm sorry, there's a typo here. It says 3 instead of R. It should be delta XR and delta YR. We rotate those quantities by the global orientation about the origin using the formula for rotating a point about the origin. And we get our final delta X and delta Y values. So all we do is plug in these values and we get it. And that's it. Combining all these different formulas together, you have a system that enables you to figure out your X and Y location on the field just using the values from these 3 odometry wheels. And just to reiterate, right, we just calculated a way or figured out a way to calculate the changes in X and Y on the global field. But these are just changes. We still have to maintain an overall position. So like we mentioned earlier, we're adding these continually to the initial position. And this is running several times a second to produce an accurate measure. And it all rests on the assumption that at very small time scales, the motor speeds are constant, which in fact they are. So everything's happening on very small time scales. It's constantly repeated. What about sources for error in odometry? Well, there's obviously mechanical sources for errors. You could have lopsided wheels, build defects, or bumpy field. That you're going to have to figure out through extensive testing and ensuring that your code is bug-free. Also just testing the wheels themselves without odometry. You could have hardware issues, slow update times, potential sensor delay. And you could have software issues, slow update times, measurement imprecision, and if you're trying to do multi-threading, which we can address later if you have questions, these are all important sources for error. Uh, Odometry is very important in FTC once you want to try doing more advanced or robust or adaptable things in your autonomous or even teleop programs. When you want dynamic movement, what's known as a positional PID, uh, algorithms that can actually drive the robot for you. So all you have to do is specify the point that you want to go to, and the robot figures out a path there and goes there itself. Algorithms like pathfinding, obstacle avoidance, peer pursuit, model predictive control, all those algorithms generally require odometry to be useful for you. So they build on top of what we've already defined here. But the good news is that there's generally a lot of libraries that handle these things for you. So the map that we've defined here is actually abstracted away in a lot of libraries that FTC teams use. However, it's still good to understand some of them. To briefly go over them, we have positional PID controller, which use a combination of X, Y, and turn PIDs to let the robot move to a specific location on the field. You have peer pursuit, which lets a robot follow a predetermined route. So you set certain waypoints on the field. Those are these black points you can see here. And the robot figures out automatically how to get there. And it uses the data from your odometry to calculate whether it's reached the destination or not. So if the robot gets pushed off the path by another robot or it hits on an obstacle, it can actually figure out how to get back on the path on its own. You have pathfinding or obstacle avoidance. These are algorithms that let you programmatically identify routes to different destinations. And instead of having to program your robot, telling it whether you have to move forward, move left, move right to reach a certain point, the robot will figure it out on its own from wherever it is on the field. And it can be combined with motion controllers like PID or peer pursuit. So in conclusion, what we went over is odometry purpose, encoder measurements, converting wheel turns, encoder movements, the math overview, and applications. And there is some example code that I've linked to right here, which I can also put the link in the chat if that's useful. And yeah, that about summarizes odometry. If you guys have any questions, feel free to ask them, and thank you for listening.
Rohan, I have a question about PID after you get your odometry to work.
Yeah.
So like you said, there was like some libraries that could help with that. Do you guys like use any, and if so, which ones would you like recommend?
Yeah, great question. So we actually don't use a positional PID. Have you heard of a library called Roadrunner? Or
Yeah, but I don't really know what it is.
okay, Roadrunner. There's a lot of really great tutorials online. We can also follow up in the FTC Discord. But essentially, what it does is it actually handles this odometry math for you. All you have to do is provide it your encoders in code, and it'll calculate odometry, and it can actually do calculate how to follow certain paths. So you can provide it certain paths you want it to follow in autonomous, and it'll calculate how to follow them exactly. So it's a very useful library. All you have to do is learn how to use it, which there's extensive tutorials online, and I can give you some links if that would be helpful. Yeah.
Okay.
Hey Rohan, can I post the getting started with a Roadrunner link?
Yeah. So if anybody else has any questions, feel free to ask. But I'll put these slides in the chat in case they're useful to anybody, and we can.
Rohan?
Yeah.
one thing, does everybody understand how this all fits together into an autonomous routine? In other words, you've shown all the tools and how to use them, but like just a real high level of where you would use what, walking through like this year's game a little bit.
Yeah, yeah, definitely.
Okay, thanks.
Yeah. So for this year's game, maybe I'll open a picture
Yeah.
to do that right here. Yeah, so for this year's game, especially in autonomous, what's good is that a lot of the movement is restricted, meaning that you don't have to move around a lot on the field. So wherever you start here at the start lines, uh, you can get pretty far in autonomous without using something like odometry. And this might be overkill for certain applications you're looking for, just like pushing the wobble goal towards a certain point, or trying to detect the navigation images, or shoot something in the tower, even in teleop. However, where odometry becomes useful is when you start doing a lot more movements in autonomous. So this is for especially if you're interested in trying to shoot some of the rings in autonomous, or gather different rings in autonomous. So if you're trying to pick up intake the rings on the starter stack and try shooting them, that's where odometry will come especially useful, because you're going to need precise positioning to handle shooting that, and account for any variability in other robots potentially pushing you around, or the stack being slightly inconsistent one way or another. Odometry, by knowing your position, you can counteract those issues. Just because you know your position, and you can say you can tell how far off you are from the point you want to be. But in most cases for this game, you generally won't need to use odometry for the more basic tasks. Not even the more basic tasks, but for most of the tasks, and even teleop. So, yeah. If you have any questions with that, feel free to ask.
Hey, Rohan.
Yeah.
I know this is a tiny bit off topic, but I'm going to just throw out the warning that this is the virtual game, the remote game. Down the line, the state championships will be, or we're aiming to trying to do them in a traditional fashion. And so it would be a full size field. So there are slight differences, but not, you have to coordinate with your partners. One thing I would recommend is understanding what your capabilities are and what your partner's capabilities are when you want to run autonomous, because you can't both do this all the autonomous. That's all.
And if there's anything else you guys want to discuss or ask, we can discuss that now if you'd like.
Rohan, if no one has any other questions, could you talk a little bit about like Roadrunner and like basically what you need to use it and what it can do for you?
Yeah, let's give me 1 second. I'll try to find a link just to provide a few things that might make it easier for discussion. Roadrunner. So do you see that link, Vincent?
Yeah.
Right. So, I mean, the requirements for Roadrunner, generally speaking, is you need to have odometry wheels on your robot, and you need to have encoders on all 4 of your wheels so that you can precisely control their movement in most cases. And that's, to the best of my knowledge, that's about it. I mean, using those odometry wheels and encoders on your wheels, all you have to do is tune a few constants. Roadrunner has a few things that you have to tune, kind of like a PID, if you're familiar with that. And once you get those things tuned correctly for your robot configuration, you're good to go. And the Roadrunner library is very intuitive to use past that point.
Okay. But so like for this year, because you're shooting things, you probably need encoders for like your shooters, right?
Right.
So if odometry takes 3 encoders and your motors take 4 more, that's probably too many. So like what would be an alternative, I guess? Like right now, we're trying to just use our odometry to run to specific positions, right? But that's without any encoders on the motors.
Yeah. But correct me if I'm wrong here, but you have 3 encoders for the odometry wheels, and then 1 encoder for the shooter, right?
It depends how many motors we use for the shooter.
Oh, I see. Okay.
Because I'm not sure if I want to take that away from the shooters.
Yeah. So actually, Roadrunner enables you to still use the library without drive encoders. The reason I didn't mention that earlier is because you have risk for reduced accuracy, but you can actually use Roadrunner without drive encoders. You can see how that works for you, but the library does work with that. Yeah, without drive encoders. Here, I can put a link right here. That might be helpful. Does that address your question, Vincent?
Yeah.